Good morning, afternoon, or evening, Prof. We are group P7-1 and welcome to our presentation of our game engine. Our group consists of me, Joshua, Jake, Urshaf, Zuo-En, Fabian, and Zhengxu. This presentation aims to showcase and explain our game engine design and implementation, and we will have a short demo at the end to explain the relationships. We have made a modular component-based architecture around common managers that will come together to make up the game engine. We have applied OOP principles such as abstraction in template classes such as entity and scene, polymorphism in overriding functions provided by a parent class, inheritance by extending a child class, and encapsulation by setting class attributes to private, hiding internal details and exposing only necessary information. It is also designed for reusability and scalability by reducing development time, promoting consistency of code across developers' projects, leveraging existing code and assets from the game engine, and made adaptable to changing requirements. Our game engine is made of the following components: the main game class, which handles the simulation lifecycle, a scene manager to manage different scenes in the game, an entity manager to manage entity rendering and creation, a collision manager for resolvement of collisions between entities, a behavior manager that manages entity behaviors and AI controls, and an I/O manager to handle input from various devices and have a unified input interface for the game. The I/O manager captures input from user devices such as their keyboard to translate user input to actions in the game. To do this, we have made it such that it uses the behavior manager to access the game logic, ensuring a clear separation between input-related functions and game entity control functions. This instance of the behavior manager is also reused from the main game class, so the instance is synchronized across all managers using it. Next, I'll pass the time over to Ashaf, who will talk about the scene manager.
Thanks, Joshua. My name is Shahul Hamid Mohamed Ishad, and I'll be talking about the Scene Manager. The Scene Manager implements screen interface provided by libgdx. It handles separate screens and calls many methods defined in the interface at various points in the screen's lifecycle. Different input processors are set to detect inputs from the user's input device in various scenes. It also uses Entity Manager to render entities in specific scenes. Without further ado, let's take a look at the Scene Manager class. Here is an example of the Scene Manager class. The Scene Manager class implements the screen interface. It's also declared as an abstract class, as it provides a blueprint for subclasses to provide its own implementations. In this instance here, the Scene Manager class takes in the game instance as its parameter. This allows the Scene Manager to control the game. After the constructor, these are the following methods which will then be overridden in the main menu scene.java class, as well as the level scene.java class. We shall then provide its own implementation tailoring to the specific needs for that particular scene. This then enhances reusability and extensibility as it minimizes boilerplate coding and provides a common functionalities for multiple scenes. Without further ado, I'll now pass on the time to Jake, who will talk more about the behavior manager in the following slide.
Thanks, Shaul. I'm Jake. So now I'll be going through on behavior manager. The behavior manager directly creates and controls the movement of entities through its methods. It combines entity movement related logic, such as player controls and AI controls, into one manager. This encapsulation of movement logic within the manager allows for a centralized point of control over the entity dynamics, thus facilitating adjustments and enhancements to movement algorithms. It also allows the interaction between entities and ensure that they remain within the play area. Moving on to the code. The behavior manager adopts the singleton design pattern to ensure that there is only one instance of this class throughout the game. The private constructor prevents instantiation from outside the class. The getInstance method provides a global access point to the instance and ensures that the instance is only created once. The updateDroplet method updates the position of the droplet based on its speed and handles resetting the droplet's position when it reaches the bottom of the screen. It encapsulates the logic necessary for managing the life cycle and behavior of droplets. These methods are responsible for moving an entity in the 4 cardinal directions up, down, left, and right. They work by adjusting the entity's position along the X or Y axis based on the entity's current speed. They provide a straightforward way to implement movement, making it easy to apply consistent movement logic across different types of entities. Handle collision method manages the interaction between two entities when they collide. The method calculates the position of both entities and applies a simple logic to simulate a recoil effect. And the handle border method ensures that player entity does not move outside the game designated play area. So to summarize, the behavior manager class serves as a centralized hub for managing entity behavior within a game, streamlining the process of updating and refining the game's mechanics by decoupling the logic for movement, collision handling, and boundary management from the representations of entities. It exemplifies a widely adopted approach in game development aimed at enhancing code-based cleanliness and maintainability. This architecture choice not only facilitates easier modifications and expansions of game rules, but it also ensures that essential game mechanics are implemented in a coherent and organized manner. Through this unified management system, the behavior manager effectively simplifies the complexities associated with diverse entity interactions, making it an integral component in the development of engaging and dynamic game environments. With that, I'll pass my time on to Zuan.
My name is Rowan and I'll be talking about the collision manager. The collision manager is responsible for resolving collisions between entities. It consists of if statements, which check for collisions between another entity or the border, then calls for specific methods to resolve the collision. To detect entities or the border coming into contact with one another, methods such as isCollide and detectBorder are present in the iCollidable interface. The collidable entity class will then implement the iCollidable interface. To resolve the collisions that have been detected, methods in the behavior manager will be called, like handle collision and handle border, as explained by Jake previously. Even though the non-collidable entity class is not used in our demonstration, we felt that our game engine would have a better design if we have the possibility of including entities without the iCollidable methods, so that not all entities must have iCollidable methods. Now I'll move on to the code. In the collision manager, we have collide droplet and collide border. The if statement checks if the collision is true, and if it is, it calls methods that are in behavior manager as seen here. In the iCollidable interface, we have isCollide and detectBorder, and it is implemented by collidable entity. Now I'll move the time on to Zhengxu.
Thank you, Zuan. Hi, I'm Zhen Xu. Now I'll be talking about Entity Manager. Entity Manager serves as a central hub for managing games entity. It adopts the singleton design pattern, which ensures that only one instance of entity can exist throughout the game's lifecycle. This will save resources and ensures consistent management. Entity Manager encapsulates functions that are used for handling entities, example, instantiation, rendering, and updating. After creating an entity, it will be added into the list in Entity Manager, and by separating entity behavior from an Entity Manager, it allows for greater flexibility and specialization. Next will be the entity class. Entity class serves as a base structure for all entities in the game. Base structure consists of common properties and behavior if specialized entities is required. Entity can be created while inheriting the common properties and behavior. This enhances the code's reusability and consistency of the code. And by abstracting the entity class, it enforces a consistent structure for all entities, but not limiting additional behavior. And now I'll be going through the codes. You can see in the codes, getInstance instantiates the entity manager's instance and also ensures that only one instance is allowed throughout the game's lifecycle. This showcases the singleton design pattern that I mentioned earlier. Next will be functions like create, renders, and updates. These are entity handling functions, but no behavior functions can be seen here as it is separated from entity manager, which will provide greater flexibility and specialization. Then there is also list structure, which in this case collates all the droplets entity together for efficient access and flexibility in manipulating the behavior of droplets in Behavior Manager. And now I'll be talking about entity class. As you can see, the structure of the entity class consists of X, Y, speed, width, and height. These are common attributes that all entities must adhere to. It keeps the field private and provides getter and setter, which you can see in this case, for control access. And now I'll be passing on to Fabian.
Thank you, Zhenxu. My name is Fabian. Now moving on to the design patterns and reusability, the components in our game engine inherits the properties and behavior from other classes, facilitating reusability in our code. The code encapsulates different functionalities, thus promoting modularity and code maintainability, resulting in less duplicate code. We utilize features included in the libgdx framework, such as game class and screen interface, to assist in the management of scenes. Implementation of concepts such as abstraction increases the scalability of our game engine, as it makes intricate systems much easier to handle, and thus greater importance can be placed on our code. Through the implementation of inheritance and polymorphism, it makes our code more flexible to changing requirements in the event of needing to modify it. Now moving on to our demo. When the start button is clicked, the listener in the scene manager transits scenes from the main menu to the game. As you can see, the bucket moves left and right when pressing A and D respectively. However, when it is detected that the player model, in this case the bucket, reaches the border of the screen, the behavior manager will prevent it from moving off. Furthermore, as you can see, when it is detected when the droplets collide with the bucket, the collision manager removes the droplets and increases the player's score. So, how does it work? After the entity manager is instantiated in the level scene, its methods are called to create, render, and update the entities in the stage. The I/O manager checks for inputs on the keyboards pressed and invokes the respective methods in the behavior manager to move the player. Finally, when any collision made by the collidable entity is detected, it will be handled by the collision manager, such as when the droplet comes into contact with the bucket. With that, we have reached the end of our presentation. Thank you for your time.